That?
With the, yeah, with the vector.
Yeah, angular velocity, that's what I was pointing out.
Yeah, they said angular speed. Gotcha.
Angular velocity. Now, we have, and so what's happening is that we have some initial angular, or some initial moment of inertia. There should be a final there. When I brought my arms in, I am decreasing my moment of inertia, so I goes down. And then going along with what Jacob said, the inverse relationship, omega goes up. So I'm spinning faster. Now let's take a look at a more complex problem. So we look at angular momentum. Angular momentum being I omega. I have a long thin rod of length, let's make it 3 meters. I have some point mass here. Let's make this 2 kilograms. Let's make the rod 1 kilogram. And the mass is cruising along, and it's going to hit the rod at this point right here, which is 2.5 meters from the pivot point. The object is going to hit the rod in a perfectly inelastic collision. If you need more of a visual, imagine you're slinging putty at a meter stick that's hanging down. Now, why would you do that? Because it's physics, and that's the kind of thing that you do. So why don't we start out with, if I hit that, how far is that thing going to swing? How high up will it swing? So I guess the question is, how high up will rod putty combination swing up? Actually, I'm going to change that slightly. For those of you who've written this down, I appreciate that, but sorry about this. The rod putty combo will swing up until the rod is horizontal. How fast does the putty need to be going initially? Parenthetically, when it hits the rod. Assume,
Sorry, keep going.
assume putty hits rod at a 90-degree angle. If you have issues with the fact that there is gravitational pull acting on these things, if you have issue with the fact that how can that thing be going straight if there's gravitational pull acting on it, we can imagine a scenario where we've got some sort of gun right there, and that I just showed the path of the putty, but we have a gun right there that's going to shoot at it, or we launch it from down here, and that just happens to be the key when it's traveling in that direction. All right, questions about what the problem is asking?
So is it, how high?
How fast? So I've got a long thin rod, putty comes along, it hits it, this thing's gonna swing up to there. So how fast does does the putty need to be going initially in order for this thing to swing up to there?
Is this gonna have anything to do with like angular velocity? I mean, obviously we have like our angular momentum formula up there, but.
Yes, it has something to do with angular momentum.
Okay.
Conservation of linear momentum here would be very difficult because the rod, yeah, it's not like it's gonna hit the rod and the whole thing's gonna be moving like that, like in a chapter 7 problem, or 8, whatever number it is. 8. All right, we have a collision here, perfectly inelastic collision. And I think I might have said it already, but what is perfectly inelastic collision?
They like stick together.
All right. Momentum is conserved. Angular momentum is also conserved. Another reason why going with regular momentum being conserved in this particular situation is I do have putty and I have the rod here, but I also have an additional force acting on the rod at this point. And so I'm looking more towards angular momentum because any force acting up here is ultimately exerting no torque whatsoever. So I know L initial equals L final. So, well, I have two objects. I have the angular momentum of the rod, initial, plus angular momentum of the putty, initial, is equal to angular momentum of the rod putty, final. So this would be the moment of inertia of the rod times omega rod initial plus moment of inertia of putty initial, omega putty initial, is equal to moment of inertia rod putty times omega rod putty final. So just taking it down piece by piece. Total angular momentum is just the angular momentum of one thing plus that of the other. Same with pretty much total of anything is just the sum of all the bits. Now we can eliminate some of this already, but I am going to ask for some information that if I were actually working out this problem on some sort of assessment, I would immediately just get rid of it, not worry about it. But I am going to worry about it right now. What is the moment of inertia of the rod rotating about its endpoint?
He's 0, since it's not moving yet.
All right. That would,
Or
did I say
sorry.
moment of inertia or angular momentum?
You said moment of inertia.
Yeah, moment of inertia is not 0, the angular momentum is 0. That's what I mean by, we could have
Okay.
immediately eliminated this
But
term
then-
right here.
But then we wouldn't know why, because I wouldn't have asked. Yeah.
However, all right, so times 0. But what's the formula for the moment of inertia of a long thin rod rotating about its
So,
endpoint?
was that the 112?
It's all 1/3.
Oh,
1/12 is about the center.
Okay.
And that's for the rod. So if on a quiz or test, you're not sure, what would you do?
Not sure about what.
If you're not sure what the formula is, what would you do?
Oh, ask.
There's one way.
Look through the formulas.
There's another one. Yeah, I'm not expecting you to have them memorized. It's just, it's nice if you know them, but not expected. Moment of inertia of the putty. I have something traveling in a straight line. What is its moment of inertia?
2 kilograms, it's max?
That would be the mass, but that's not the moment of inertia. Let's go back to our formula, where it all started. Moment of inertia is just the sum of all the mr squareds. If I have this single piece of putty that is shooting off to the right there, how many bits of mass do I have? And I specifically said it's a point mass, which means that its size is, I'm not worried about the size of it. What would R be?
0.
What is R?
It's the distance from the end to the axis of rotation.
Right, okay, from the bit of mass to the axis of rotation. What is that distance?
Is this before it hits the rod or right as it hits the rod?
All right, so when you say before, how much before are you thinking?
Any amount before it hits the rod.
Yeah, it's not just any amount. We do have to look at it of just before the collision and just after the collision.
Okay.
So anything that happens prior to that instant before it gets there, we don't know, we don't care.
Then the R would be 2.5 meters.
Right. So it ultimately would be mass of the putty times that distance, and let's come up with some name for it. See, L did L for the whole thing. I'm just gonna call this something clever like R sub P. Yeah. And omega?
That's what we're solving for, right?
No, well, actually, we're solving for speed,
Oh,
linear speed.
Would that be just V?
would it
Not just V.
be V over 2.5?
Yeah. So this would be V over R sub P.
RCP, yeah.
Let's set up a convention here. In what direction is my angular momentum?
Into the board.
Yes. Now, if we look at this bit right here, I recognize we haven't done the right-hand side of the equation yet. We have, so the angular momentum of the putty initially. It's still about the same axis of rotation right there at the top. This would be mass of the putty. Well, one of these R's is going to cancel out with one of those, so this becomes RP times V in the negative K hat direction. I'm going to rearrange this slightly. Negative MPV times RP. K hat. And what is that?
That is momentum.
Yeah.
It is. I probably should throw subscripts in here. Getting a little bit slack with my notation here. That's my initial momentum of the putty. So P sub PI. Recognize that oftentimes we don't need to go through this route, but especially if you're dealing with point particles or things that there's not a lot of variety or depth of speed, this is just R cross P. If I think about that, I have my momentum going in this direction, so in the negative I hat direction. R is a vector from the axis of symmetry to where the action's happening. It's in the negative J hat direction. So I have negative J hat cross negative I hat, which would be
One.
not one. Don't forget, it's a vector product. We should have a vector in the end. And if I'm interpreting what I'm seeing, Jacob, right hand. It looks like you're doing your left hand.
Oh, no, I was just
Just
like,
stretching, okay.
yeah.
I misinterpreted. When you're doing cross products, I got my I, J, and K set up over there.
Do you end up with J hat?
If I do what? How, is that for the whole thing, K hat?
Yeah,
How'd you get that?
I don't know, I just saw like negative J hat, negative I hat, and I was like, positive K hat, I don't know.
Well, the negative times negative is indeed positive, so that would be the same as J hat cross I hat.
We'd end up with a vector, you said?
You would end up with a vector.
Would it not be negative?
It would be negative K hat. You were close. Hand in the direction of the first vector, J. You want to have it so your fingers bend towards the second vector, I. Thumb points into the board, which is the negative K hat direction.
Oh, okay.
Or, so I, J, K. Go in that direction, it's positive, go in that direction, it's negative, and we did J cross I, going to the left, you get a negative K.
Wait, but it is negative, so wouldn't it, we start with J hat in the negative direction, so.
Okay, if you're gonna go that route, there are several
I
ways of
guess
doing
it's
it.
the same thing, right?
You'd have negative J hat this way, negative I hat that way.
It would still be going this way, yeah,
Yeah.
into the board.
Wait, so
I
if you-
hope so.
If you have a positive J hat, negative I hat, you'd get positive J hat?
Yes,
Okay.
which would be interpreted, I think you said negative J hat, positive I hat. Given our convention, that would be the putty going that direction,
Okay.
which would get it to spin the other way. Which makes physical sense. I hit this thing from that side, it's gonna go this way, and hit from this side, it's gonna go that way. Physicists and mathematicians got together and formalized it. And any left-handed person there, they just ignored.
Yeah, so, how did you get so you see the second equation next to the plus sign, so, yeah, but, go down. Yeah, that, so, how did you get that? So I see how you got the m r squared, cause that's for the moment of inertia, but what's that second part?
That goes with the fact that omega, the angular velocity, even though that's traveling in the putty's traveling in a straight line, at that moment right there, with that as sort of the axis of rotation, it is spinning, it's going, would be clockwise. So, thumb points into the board. So, the direction of the angular momentum is the negative K hat into the board. And this V over R comes from the equation of V is equal to omega R,
Okay,
omega is equal to V over R.
so, but we don't know the.
No, we don't.
Okay.
But we will. And that is gonna be equal to the total moment of inertia times RP final. And that's just after the collision. That's not at the end of the problem when the bar is horizontal. All right, so let's do the right-hand side now. Moment of inertia of the rod and putty combination.
What would be the mass of the rod plus the mass of the putty first?
And what are you gonna do with that?
Multiply it by the angular velocity, that's the answer.
Oh, times that, no, but define, it sounded like you were just using the mass, the combined mass for this.
As far as I know, because they're treated as one object if it's perfectly inelastic.
Correct. So they have the same angular velocity, but to find the moment of inertia, to find this, what would you do?
I guess I don't know. I guess I would have guessed 3 kilograms since that would be their combined mass.
Yeah, we have to somehow bring distance into it. Moment of inertia's got that R in there.
Would it, would you use the 1/3 ml squared, you just, for the m, you just use both masses?
We need a new coefficient, wouldn't we?
Or,
Potentially, depends on how complicated you wanna make it. It's not as, it's, in my opinion, simpler than what you were suggesting. And definitely simpler than coming up with just a new coefficient that way.
I mean, the mass we're adding to it is twice the mass of the original rod, so it's a pretty big redistribution of mass.
Yeah, but the rod is still, I didn't state it, it was supposed to be understood, but the rod is uniformly distributed. And suddenly you have this big clump stuck on it. And now harken back to the formula for moment of inertia. What does this capital sigma in front of that right hand mean?
Summation.
Yes. So the moment of inertia of the combination is 1/3 mass of rod times length of rod squared plus mass of putty times